So hopefully people online can hear me. And hi to everybody in the room. This is the 52nd part of this 52nd series of the Martin Center research seminars, organized by Michael Salka, Amada, Joey, and myself. And for the inaugural seminar for this term, we're really delighted to have Professor Dafna Fisher-Gewirtzman, who's the chair of architecture program at the Faculty of Architecture and
former
chair of the architecture program at the Faculty of Architecture and Town Planning at Technion. She serves as the director of VisLab, the visualization laboratory at the faculty, and she previously served as head of the architecture school and vice dean for students. Dafna's academic life is driven by her belief in a sustainable, vibrant, and healthy environment, and therefore strives to combine the areas of academic activities in order to generate synergy among them while engaging in significant doing that will ultimately heighten the quality of life. She achieved international recognition for her research in visual analysis and simulation of urban and architectural space related to human perception and behaviour. So we're super happy to have you here, Dafna. There'll be time for Q&A at the end, but without further ado, I'm going to let you expand on promises to be a very exciting and relevant topic for all of us here. So welcome everybody. Dafna.
Thank you, Sam. Thank you very much, Sam, and everybody that was into organizing this very happy opportunity for me. So I'm very happy to be here and share with you my research, well, at least part of it. And today I'll talk about my journey towards developing predictive models, focusing on human urban phenomena like perceived density and wayfinding. Yeah. So I'll start with a brief introduction to my lab. And today the main three anchors of research are, as you see on the left, developing analytical models and tools simulating and predicting human behavior, and then conducting experiments to study the influence of variant spatial parameters on human well-being, perceived density, wayfinding, and more. And of course, assessing these models through experiments in VR. And last but not least, which I'm not going to share with you today, is developing generative tools based on the above. So in my talk today, I'll focus on urban perceived density and wayfinding for the aging brain. So urban density, as we perceive it. My research motivation is led by densification processes in many urban areas in the world and the way that urban density is perceived. We know that soon 70% of the world population will live in urban areas, and the term density is becoming more and more urgent. The question for me was and is how to design and densify so that urban well-being will not be damaged, and how can we quantify it and predict it. So we already know that dwellers' well-being is greatly influenced by urban design and that physical attributes influence perception, emotions, and behavior. Urban density, we definitely do not want to feel, and we definitely want to resist. And this is another photograph by Michael Wolff and my edition of a scary movie. This is urban density in a different scale, emphasizing the multi-scale challenges, the multi-scale challenges of density. And please consider the visual noise you see in this micro apartment. So it's not just the scale or size, but more spatial parameters that influence us in all scales. And this is where it all began for me in my PhD about 25 years ago. So there are many density measures, but I was looking for something to measure that would indicate the perceived density, an objective measure indicating a subjective perception or experience. And I call the model the spatial openness index, which is defined as the measured volume of visible space reinforcing the perceived density. An analytical model assessed by experiments. So here you see several groups of dense built compounds that were part of the research of my PhD, all with the same built volume. They were once ranked by participants in a desktop experiment regarding their perceived density, and once ranked by their measured spatial openness index. Again, the volume of visible space that several years later, it was referred by Morello and Ratti as the 3D isovist. I'm sure that all of you are, you know what isovists are, and of course now a lot of companies and research groups also have this opportunity of 3D isovists. Now, in most of the groups, the most compact and the most decomposed were perceived as the densest, and their spatial openness index was the lowest. So visibility was directly correlated with the perceived density. Currently, the spatial openness index is based on 3D raycasting, calculating the accumulated lines of sight on each viewpoint assigned on the building facade. And the higher the visibility, on the lower image on the right, you can see the bluish is the spatial openness index is the highest and the lowest perceived density. And on the left, you see comparative analysis of spatial openness index for alternative morphologies in a specific urban environment, all with the same density, volumetric density. And this is taken out of our demo in preparation, which we plan to work with practitioners, some of our previous students that are now have fantastic practices, and we want to work with them to see how they can actually use our models. So based on the spatial openness index, I wanted to develop a model predicting the perceived density of pedestrians walking along an urban route. And in this case, you see the Rothschild Boulevard in Tel Aviv, and you see on top, you see two directions of our agents walking. And so to simulate pedestrian visibility, we spread the viewpoints along predefined route. And since visibility is directional in this case, the 3D raycasting is in the walking direction. So that was the starting point of what we call today dynamic visibility analysis, which is of course a 3D visibility analysis. We conducted a systematic study, created 16 varying paths for the same location and measured their visibility. Now, the graphs show visibility quantification along 100 viewpoints. So each viewpoint is static, and then we measure. But then since we have a lot of viewpoints along the path, we can say that it's what our participant, or I mean human participants, would actually feel when they're walking along. So these are just two examples. What you see here, the videos out of the 16. So you see an agent walking in the center of the boulevard on the left, and an agent walking on the sidewalk. And both have the options with trees and long, low buildings. So to assess the model, we conducted an experiment where our participants ranked the perceived density of the same virtual environments based on manipulations of the Rothschild Boulevard in Tel Aviv. So we had existing buildings, which are 3 to 5 floors, and also tall additions to these existing buildings, with and without massive trees and greenery, and simulation of walking on the sidewalks and in the center of the boulevard. And the results in general show that low buildings with or without trees were perceived as low perceived density, and tall buildings without trees were perceived as the densest, which is the reddish. But tall buildings with trees and walking in the center of the boulevard was perceived as less dense than, without the trees. So we realized that trees matter, greenery matter. Now, if we look at the visibility calculations versus perceived density, we see that the first 5 paths were ranked exactly the same. High visibility calculations were perceived as lowest perceived density. But see the red dashed lines showing very different ranking. So at the beginning, we were really worried that we get different ranking because we like correlations. But then look at the A2, the reddish, with the tall buildings that had quite an average visibility calculation measured from the center of the boulevard, but were perceived as the densest option by participants. Okay. And the purple had the lowest visibility calculation. Okay. And it was perceived not as dense, and probably because of the trees. So that is when we realized that we have to give weights to different spatial parameters, and that's in a different talk, but you can read the paper, of course. Now, this study, we examined the impact of height of buildings and presence of greenery on human stress. And this was a collaboration with Semi Haldan and Clayton Curtis while I was on sabbatical at NYU. We used EEG measurements to quantify the impact of these characteristics using virtual environments, actually the same environments I had in my previous studies. So results show that subjects felt the most relaxed when the urban settings were composed of short buildings with greenery and vice versa. So now we wanted to explore the relationship between urban morphology and the perceived visible space from the pedestrian's perspective. We ran the DVA, the dynamic visibility analysis, on variant morphologies around the world. And this is an example of a comparison between 4 different urban environments. All were similar areas and the same length of pedestrian route, which was 1 kilometer. And in Manhattan, top left, Barcelona down left, Venice, and the interlace in Singapore. And the reason why the interlace was part of the case studies was because the first time I showed it, it was in a conference in Singapore. Because this is not a typical downtown in Singapore, just saying. So if we look at the graphs, we can see that we get unique patterns of visibility to each path. And please look at the Barcelona, the second from the top. And you see that in a way, it seemed to me like a healthy heartbeat, Like whenever you get to an interchange, you see much more sky view, and then you go again to the route. And there's something comforting by knowing that it's coming, and then it will come again, and it will come again, and come again. And remember this for the next slides. So at the same time, we conducted an experiment presenting a simulation of the same paths we analyzed in a controlled environment to find out the participants' preferences. Sorry. We expanded the questions to well-being parameters in addition to the perceived density question or ranking. So we referred to perceptions of safety, happiness, relaxation, tension, illuminated dark environments, etc. And you see the interlace on the left and Barcelona on the right. And just to say that we created typical facades. It wasn't exactly the facades, but we looked at pictures from Google Street and tried to fix something that would be typical. And the funny thing was, the funny story is that one of our participants, when she ended the study, she finished and then she said, relating to Barcelona. She said, oh, I love Paris. So there's something about the typicality of, I don't know, maybe European downtown. So again, since we wanted to see the influence of facades on the evaluations, we had a control group of participants with blank facades. We assumed that the aesthetics of facades, materiality, openings, geometry, and so forth would make a difference. And the results were that most environments with the facades had more positive evaluations than the same environments with blank facades. And in general, Barcelona got the highest score out of the 7 urban environments that we studied. We also had parts of Tokyo and 2 environments in Israel, in Haifa and in southern of Tel Aviv. Environments with lower perceived density were also ranked as safer, more illuminated, and more attractive in general. And just to say that Barcelona was not the environment that had the lowest density. It was right in the middle, but still people felt the lowest perceived density in this area of Barcelona, which was really, really interesting. So after several iterations of experiments assessing the DVA model and calibrating the model, we were confident that it can simulate and predict the pedestrian visual perception, the perceived density, and additional well-being parameters. Now, the DVA quantifies the accumulated lines of sight along predefined route to every predefined category. And here you see a category of sky view, residential buildings, commercial buildings, offices, hotels, public buildings, and parks and greenery in general. But of course, the user can decide which are the parameters geometrically that you want to actually test. Now, on the graph on the lower left shows the visibility calculation along the path, and it's measuring every 10 meters along 1 kilometer. So you can see where you have more sky view, more specific buildings, and where you have more greenery, etc. Now, another variation of this mesoscale analysis is the DVA interaction, which is focused on vertical thresholds based on Young-Gale's definitions, types of facades, and building functions as we had in the regular, what we call regular DVA, indicating potential interactions of pedestrians with events or other people along the street, or, I mean, shops and so forth. Now, just to say that interaction or potential interaction is known to contribute to the urban well-being and also indirectly influencing the perceived density. And just to say that calculation is a bit different since we now give advantage to the shorter lines of sight, in contrary to the spatial openness index or DVA, the regular DVA, where we aim at measuring the longest lines of sight, because we want to see how close we are to the shops, to nice things that we want to interact with. And this is an example of the graph relating to potential interaction along the path. And in this case, you see that the commerce, the purple color on the right, is the most dominant, and it shows that there are high potential for interaction on that specific route, positively influencing urban well-being, and of course hoping that the cafes are really nice and not something that we would want to avoid. So now moving on to the macro scale. The urban, what we call the urban spatial openness index, is a spherical raycasting on an urban size sampling grid. And the reason why it's not directional is because we want to have a kind of a general idea of what's happening in that specific grid that we're checking. So we're looking all around. And so the USOI as we call it, results are normalized to values compared to the highest possible visibility result, where we don't have any interaction with buildings or trees or anything. And I mean, the maximum is where you're like in the middle of the sea or in the middle of the desert, where you get maximum ray casting. And the result in that index ranges between 0, which is reddish, and 100% where it's blue. So here, part of Manhattan, you see that it's like in the intermediate. And here you see a comparative USOI analysis of 9 case studies. We had 3 in New York, 3 in Tel Aviv, and 3 in Zurich. Each has different urban morphology. Some have similar density, volumetric density, and some very different. Now, in this graph on the right, you see a cluster of case studies with similar volumetric density and different visibility calculations. This means that the morphology impacts the visibility and therefore impacts the perceived density. And that takes me back to my PhD, where I actually, everything was the same volumetric density, and I was playing around with a lot of different morphologies. But of course, if we look at the Midtown Manhattan, obviously volumetric density impacts the perceived density too. Now, since conducting urban spatial openness index is computationally intensive, we are developing a machine learning model to predict the perceived urban density. And this work is together with Guy Ostern, a new faculty in our School of Architecture. And he has also computer science degree, so it's very helpful, of course. Now, the data generation for the ML model are 2 heat maps, one for the building heights, the grayish one, and one for the USOI values with the colors, and we're still looking for the right colors. And this is when we're zooming out and zooming out. And here's an example of our initial training model results, and it seems to perform okay. The validation images are similar to their corresponding masks, and differences are very small and getting better, since currently we're further training the model with additional urban environments with variant morphologies, and we will present it in the next space syntax seminar in Cyprus next month. I don't know if somebody is coming there, I don't know. And our next steps are to refer to topography, which I have a good feeling about because it's still geometry. And we hope also to do it with vegetation, but that would be very difficult since we will have to think about it's more complex. So before I turn to present our work on wayfinding and navigation, I would like to present a set of experiments focusing on urban well-being, a research work by my former PhD student, Dr. Yala Tosman-Heifler. Her starting point was the existing condition of a street in Tel Aviv with a specific volumetric density that we described as X, and manipulating the densification rates as to 2 times X, 3 times, up to 6 times. So you see it here. And then with and without greenery, and with and without commerce. So you see the 4 options. So one of the main outcomes was that density rates and presence of vegetation and or commerce on street level had significant positive impact on well-being. The threshold was 4 times the existing density, meaning that participants did not feel deterioration in their well-being if the environment included massive trees or commerce on the street level, which is very interesting because we were really focused on greenery. And it appears that people, if they walk along the street and they see a nice cafe, it's almost the same for them. Anyway, so experiments took place in the lab with the white screen that you saw before. So that is when we decided to focus on variant morphology options for the density level, this 4 times the existing density. And this experiment was conducted with the Vive HTC for each participant individually. So we asked them to imagine that they're walking along the street. So they walked, and then they could jump into some of the apartments and look down to the street, and then give us their ranking or their idea of how they actually perceive the space. So the sense of well-being is higher in the environments with small and medium volume composition. That's what we got. And probably because it was provided more of a human scale, but we're not sure because we didn't ask them that question. So this is just our hypothesis. And the lowest was with a tall continuous block that you see right in the middle with the exclamation mark, environment number 4. Just to say, it's not low buildings with continuous block, it's tall buildings with a continuous block. And in general, we could divide the environments into 2 groups. Environments 3, 5, and 7 defined that the group A, with a small medium volume composition, scored higher well-being and evaluations than the environments in group B. Now we compared the experiment result to the DVA results, whereby the higher value, the higher the perceived openness, and the lower the perceived density is. And the charts show that group A offer higher sky exposure and visibility in general, meaning lower perceived density. So we were happy. Now going to the third experiment, where it focused on street sections. The one above is the boulevard. And then in the middle, you see the boulevard, or similar to the boulevard, same width, with an integrated tram lane. And the third one on the bottom is the 2-lane street, which was also the narrowest. Now, the boulevard street section provided the highest values for all well-being domains: happiness, safety, vibrancy, lowest perceived density, while the 2-lane street section presented the lowest values. Now, these are 2 videos from the third experiment focusing on street section manipulations. And on the left, you see a boulevard with the integrated tram lane, and on the right, the boulevard, where you're actually walking through the middle of the boulevard and very close to trees and, well, bumping into people, of course, in the video. Sorry about that. And this experiment was carried out with about 150 subjects on Qualtrics platform during COVID, when we couldn't invite people into the lab. But when the world opened up, we conducted the experiment with 3 groups of architecture students. We had, of course, Israeli students, French students, and Americans that came to visit. And we were interested to see if there are any cultural differences. Now, there are minor differences if you look at the graphs between the groups, but in general, you see that the tendency was very similar. And of course, in the future, we have to expand the study to normal people, not architects or students of architecture, because sometimes we think that maybe this is how we are taught to think, or how we teach our students to think. So that's the end of the perceived density and well-being, and let's move to a different model. So a grid-to-star network transformation, improving indoor wayfinding with spatial computing tools. So relating to the influence of architecture design on wayfinding. This research project is a collaboration between Dr. Marianne Merchav, a cognitive neuroscientist, and myself. And Marianne was my postdoc several years ago. And we're working also with Anat Blysen, a research fellow in my lab. So wayfinding is a process of establishing and navigating a route from a point of origin to a specific destination. It results from interaction between internal navigation skills, which we're supposed to get born with or have it along our life, and also external environmental elements where architects and urban designers can help on the second part. We focused on wayfinding for the aging brain, and our motivation was aging of global population and their declining navigation abilities, and the importance of designing and adjusting built environments to enhance spatial orientation. So, in order to find our way, we use two types of spatial reference frames. In the egocentric reference frame, we code locations relevant to ourselves. And in the allocentric reference frame, we code where things are relative to external elements. So far, attempts to improve wayfinding mainly focused on landmark-based allocentric navigation system, which relies on environmental cues such as landmarks. But we aim to improve wayfinding by strengthening route learning. So we predicted that it would be easier to form an association between a target and a route if each target can be accessed via a specific path, like in a star design, rather than a multiple alternative paths like in a grid design, which we find normally in cities. Now, since route-based learning is preserved in aging, and since older adults tend to rely on egocentric strategies compared to younger adults, we predicted that strengthening route-based navigation by star design would be particularly beneficial for older adults. So we conducted a desktop experiment and compared wayfinding preferences in two architecture designs of shopping center and in two age groups. We had 68 young adults and about 60 older adults. And the two architecture designs were identical, except for 5 additional walls marked in red in the, up on the right. And that was added to create the star design. So the yellowish lines are just to show you what's happening. I mean, I could get lost for a long time if I go in the grid design, but in the star design, I would always come back to the starting point. So we had 2 learning stages to our participants. The first was that participants were asked to just count the shops, go around. They had several minutes, just go around and count the shops. And the second learning stage was they had to walk around and find 8 shopping center logos. And then we had 2 retrieval sessions. The first was that participants were asked to go directly to a shop that were presented to them by an image. They had to find that shop specifically. And then they had, I think 8, we had 8 shops that they had to find. And we measured path lengths and the rate of non-direct paths. And the second retrieval step, we removed all the elements of the shops. We told participants that this is due to a kind of a renovation in the mall, and they had to rely on their memory. We said, yeah, you forgot your wallet, you forgot your watch, and you have to go back. Yeah, it's going under renovation, but you have to find your watch. So they had to go there. But then we did not give them also a feedback whether they have reached the target or not. So that was really interesting. Now, the results. In the learning stages, we looked at path lengths, and we found no effect of age, but a significant effect of design, with longer paths in the star design, which was very reasonable, because in the star design, you have to come back and forth. Even if you're lost, then you'd always come back to this starting point and then go around. And surprisingly, older adults did not take longer paths. For the first retrieval stage, we found no effect of design and a significant effect of age, with older adults taking longer paths to target shops, which was something that we actually expected. And similarly, looking at the rate of non-direct paths, you can see on the right an example of a direct and non-direct path to the entrance of the ice cream shop. Okay, and there was no effect of design and a significant effect of age. And at the second retrieval stage, where we emptied all shops, we found a significant effect of age with larger distance error for older adults, which was not surprising. But we also found a significant effect of design with shorter distance errors in the star-shaped configuration. So this suggests that the star design resulted in superior navigation performance for all ages, not just for us old people. So now, since this was a desktop task, it lacked self-motion cues. So to address this limitation, we currently run a follow-up immersive VR version of the study in which participants naturally walk in the virtual environment. And since we use the gallery space of the Faculty of Architecture, we had to change the design and adjust it to the physical geometry of the space, to our grid and star designs. And here you can see participants while performing the task. And this is what he sees through the VR headsets. We finished the young adult part of the experiment, and we are very encouraged since results follow up the desktop results. And we can actually say that star pathway design resulted in superior navigation performance. But of course, we are going to continue with the older adults. So now we wanted to go into the model. And our objective was to develop an automated assessment for evaluating networks in general on the scale of grid to star and the effectiveness of the network layouts, and to develop a model that can transform grid-based networks into a star-shaped configurations. We defined 4 stages. The first 2 stages, or experiments like we call them, are networks assessments, and the third is transformation from a grid to a star, and then testing the model as our final for now. Now, for the first stage, we conducted topological analysis on the centralities of the paths, computing every shortest path between all starting points and endpoints with the network, and then assess the frequency of these shortest paths traversing a specific edge or route segment. And saying that the greater this number relative to the total possible paths in the origin network, the highest the star rating of the network will be. And we employed an open source analysis tool developed by Decoding Spaces. And here on the slide, you can see very clearly the differences between the star and grid designs for both desktop and VR experiments. I'd say that the VR experiment environment is even better. And the second experiment or stage involved in analyzing a wide range of synthetic networks. These are just a few of them. We rated each network as to how close or further away from the being a star or a grid network they are. And then we went into the third stage, where we developed a method to modify existing networks into a star design by creating blockages. If you remember the reddish walls, so now we just disconnected the grid. And we did that for various synthetic configuration. And for this, we used the Galapagos plugin in Grasshopper. The goal was to find the optimal network configuration with the highest star rating. And here you have an example. On the left, A is a regular grid centrality analysis. In the center, you see when we actually run the model, when we modified the grid into a star, and when we specified the preference center to act as the star hub, relevant to what we found in the first analysis. And then on the right, you see when we did not specify any preferred center, and we get a main passage that includes several edges. So the passage is not really the idea what we thought about, but so we are more into the modifying the grid. And then we tested the model on a real case study, and this is West Side Market in Cleveland, Ohio. We actually looked in the internet and looked for, plans that could really look like public buildings with a grid. And here you see a regular grid centrality analysis on the right. And now on the left, network is referring to a specific preferred center to act as the star hub. And on the right, we let the model run without indicating a preferred center. And therefore, again, the result is the main passage that includes several edges that function as in the center of the star, which is, again, it is problematic. We aim at having a specific center. Now, here you'll see in a minute a demonstration of the transformation model running on a synthetic grid. I mean, that's like 100 times quicker than what's actually happening on our computer. And also just saying that in case we get options with isolated zones, we have to get rid of them, of course, because otherwise there are some areas that you cannot do anything, you cannot reach them, and so forth. So that's a problem. And now I will just summarize this model. So it builds on the empirical experiment results that a star route design is beneficial for all ages wayfinding. And we see that transforming a grid into a star results in structure with distinct branches, which may result in many challenges, such as the problematics of cul-de-sacs. And there are some papers by Bill Hillier regarding the problematics of cul-de-sacs in the urban area, but we are going to work on that. Now, this work is in progress, and we will present it in the next ICADE conference in September. I hope somebody from the crowd are going to be there. And currently, we're looking at the urban scale to progress our model. And of course, this idea of the cul-de-sac is going to be even more problematic in the urban area, but we're going to be very creative, I hope, to find solutions. So to wrap it up, I presented two areas of research conducted in my lab. One that has accompanied me for about 25 years, and the other from the past few years, and is in its initial stages in a way. I can probably base my approach of developing predictive models more on the research regarding perceived density, and to develop a well-established model that claims to predict human perception, behavior, and cognition. I would suggest to focus on phenomena that interest you. And then try to figure out and to define some measurable parameters. And I must say that it wasn't straightforward when I was thinking about it during my PhD. I had a lot of debates, and I tried to figure out what can you actually measure when it's a 3D perception of a person walking around space. And then when you have these measurable parameters, try to have a preliminary predictive model that is simulating the phenomena. and then test it on various scales and various case studies. This is normal, but then go back and calibrate the model. Then assess the model by multiple empirical experiments with variant experimental tools and variant potential people's profiles, because not everybody thinks like, I don't know, your students or yourself and so forth. And then again, calibrate the model. And then, of course, update the model with cutting-edge technologies. I mean, thinking about when I was doing my PhD and what's happening now, it's completely different. And then again, refine the model. And I think very important, if you're relating to how people are experiencing space, it's very important to also get practitioners' feedback on what you're doing, because otherwise you're just in academia and you're not doing any impact on reality. And of course, then adjust the model. And this is like the line is dotted since this is something that we just started to do, so I cannot say that it's working. And I think only then you can confidently claim that you have a predictive model. So I'd like to thank all of my colleagues, postdocs, PhD, MSc students, and research assistants that took part in this work. Without them, it was not possible to do all this work. And I thank you for listening. Thank you.